So for the next part, I want to introduce it in the context of a practice problem. So let's suppose that we are the first ones who are studying liquid water, and we know that at 50 degrees C, the saturation pressure is 0.124 bar. We also know what the enthalpy of vaporization is, the molar enthalpy of vaporization. Now from this information only, we want to estimate the saturation pressure at 55 C and 60 C. And of course, obviously, if we wanted to really know what the saturation pressure of water at 55 C is, we just go to the steam tables and look. But again, the goal of this is to illustrate what you would do if you did not have exhaustive data available. So let's pretend, just for sake of argument, that this is the only data that we have available for water. How would we do it? So this statement tells us that at 50 C and 0.124 bar, we have equilibrium. An equivalent statement would be that at a pressure of 1.24 bar, the boiling point of water is 50 C. That's saying the same thing. Therefore, at this temperature and pressure, we know that equilibrium exists, and we can apply our equilibrium criterion. So at 50 C and 0.124 bar, we know that the Gibbs energy of the vapor will be equal to the Gibbs free energy of the liquid by equilibrium criterion. Now we can extend that and say that the change in Gibbs free energy for the vapor will also be equal to the change of Gibbs free energy of the liquid. So as we move along this vapor pressure curve, so I'm going to sketch in kind of what we know it looks like. So this is P star or P sat, this is T. We know that in general, the vapor pressure curve looks something like this. So again, we know one point on this curve. We want to know that if we change temperature by however much, we want to be able to estimate what our vapor pressure will be. So we don't know any other points on this curve, but we know it looks something like this. So we know that if we increase temperature and we increase pressure, that we are going to have different Gibbs free energies. But if they are equal to each other, then we will be able to say that the change in Gibbs free energy for the vapor is equal to the change in Gibbs free energy of the liquid. And then we can apply the fundamental property relationship of VdP minus SdT, and we can apply the relevant subscripts. So we can say that the VdP, so the molar volume of the vapor, minus, V vapor dP saturation minus S of the vapor dt must be equal to the volume of the liquid dP saturation minus S of the liquid dt. And then we can rearrange this to get dP saturation dt. That's going to be the slope of this curve. So when vapor pressure is plotted versus T, the slope of this curve is dP sat over dt. Just as an aside, I'm going to try and keep the notation of the book, which is saying P sat. I really like the notation of other textbooks, which is P star. So I may interchange those. Just be aware, if I ever say P star, I mean P sat. But I'll try and adhere to P sat. So I want to solve for the slope. And again, the slope is P sat, dP sat over dt. So pause the video and try and solve that. So this equation looks potentially useful. The only problem is if we could use the steam tables, of course, we could look up the entropy of the vapor and the entropy of the liquid for water at whatever temperature we wanted. But remember, we can't use the steam tables for this particular problem. We're limited to only using what we have available. Notice that we have enthalpy of vaporization. We do not have entropy of vaporization. So we don't have delta S vap. We only have delta H vap. That's no problem. What we can do is relate what we want to know to what we do already know. So we want to know something about entropy, but all we have is enthalpy. So use the form of Gibbs free energy. So we know that Gibbs for liquid or for vapor, so Gibbs for vapor is equal to enthalpy of the vapor minus T times entropy of the vapor. And we also know that these are all equal at equilibrium. So Gibbs of the liquid is equal to HL minus TSL. And we can rearrange and solve for SV minus SL. Solve for SV minus SL. And we get that that is equal to HV minus HL over T, which is something we know. So the enthalpy change from vapor to the liquid is literally delta H vape over T. So in this equation where we have SV minus SL, all we have to do is substitute in this expression that we just found. So we can say dP saturation over dt is equal to delta H of vaporization over T times the molar volume of the vapor minus molar volume of the liquid. So this guy should look familiar to you, hopefully. This is something that I introduced in MEB. Remember, this is called the Clapeyron equation. And it looks like something that could be potentially useful to solving this problem and figuring out what the saturation temperature for these different, saturation pressure for these different temperatures is. So if I know that dT is 5 or 10 degrees Celsius, I should be able to evaluate what delta H vaporization over T times the change in molar volume is, and that would give me what my saturation pressure is. There's a couple of snags with this strategy. One of them is that delta H for vaporization is only known for the specific temperature and pressure. And you may remember that delta H, this should be delta H underbar, delta H of vaporization is a function of temperature. And it's a function of pressure too, function of T and P. So that's one problem. And then another problem is that, remember, we are forced to only use the information that we have. So what is the molar volume of the vapor and what is the molar volume of the liquid? How do we figure those out? So in order to get around this, we have to make another couple of simplifying assumptions. The first simplifying assumption that we'll make is that since our change in temperature is small, only 5 degrees, we're going to assume away and say that delta H of vaporization is constant over small temperature changes. So assume constant for small temperature changes. So here we only have changes in temperature of 5 and 10 degrees. We expect that the 10-degree answer is going to be a little bit less accurate than the 5-degree answer, but still it's going to allow us to solve the problem. So we'll just use the enthalpy of vaporization for the temperature and pressure that we have. Now, as for what the molar volume of the vapor and the molar volume of the liquid is, here we have to make a conceptual assumption and say that we're going to assume that the molar volume of the vapor is much, much greater than the molar volume of the liquid. This is a pretty decent assumption, right? So the space that a vapor takes up will be much greater than the space that a liquid takes up. And you could cheat and look at the steam tables and just look at any temperature and pressure for saturated water and see that the molar volume of vapor is much greater than the molar volume of liquid. So with those two assumptions in place, we can then simplify and say dP saturation dt is equal to delta H vaporization. Remember, we're going to say it's constant over T times molar volume of the vapor. However, we still don't know what the molar volume of the vapor is. We'll make a third assumption and say we're going to assume ideal behavior. If we assume ideal behavior, we can say that the molar volume of the vapor is equal to RT over P. And because we are at saturation, we're going to say that the molar volume of the vapor at saturation is equal to P saturation. So plugging this stuff in gets us dP saturation. That should be a superscript. dt is equal to delta H vaporization over RT squared divided by P saturation. All right, now we're getting somewhere. We can get to the point where we can finally integrate this thing. So I'm going to separate variables. So I will bring the P saturation over to the other side to get dP saturation over P saturation, and bring the dt over to the other side. So delta H vaporization over R times 1 over T squared dt. And I wrote it like this because delta H vaporization we assumed constant, R is a constant, so I can bring it outside of the integral. Now I can integrate this expression to evaluate what is going to happen. So integral of 1 over P saturation dP saturation is ln of P saturation is equal to delta H vaporization over R and then minus 1 over T. So writing that a little bit neater gives me, and when we apply our limits of integration, so P sat 1 to P sat 2, and T1 to T2, we will end up with something that again should look very familiar from your time in MEB, which is the Clausius-Clapeyron equation. So P sat 2 over P sat 1 is equal to minus delta HV over R, parentheses 1 over T2 minus 1 over T1. This, as I said, is the Clausius-Clapeyron equation. And recall the assumptions that went into it. So importantly, in order to assume Clausius-Clapeyron, you must assume that delta H vaporization is constant. You must also assume that the molar volume of the vapor is much, much greater than the molar volume of the liquid. And third thing you must assume is ideal gas behavior. If you can assume these three things, you can use the Clausius-Clapeyron equation. And this is something that is now usable, right? I know what the enthalpy of vaporization is. I know what the gas constant is. It didn't explicitly say it in the problem statement, but I'll assume that constants are known. I can plug in T2, T1, and P-sat1, and that will allow me to solve for P-sat2. So I'm not going to show you the exact calculations. I'm just going to show you the answers of what we get. The saturation pressure at 55 C would be 0.158 bar, and at 60 C would be 0.2 even bar. And looking up what these values are from the steam table, so from steam table, so now that we have our final answer, this is what they asked us to solve. From steam table, we can look up and see how accurate these answers were. And if you look up what the saturation pressure at 55 C is, you find that it's 0.158 bar, which is exactly the same. And for 60 C, it is 0.199 bar. So these estimates are pretty good. This is again because my temperature interval is small, such that I could assume that the enthalpy of vaporization was constant. I have low pressures, so that means my ideal gas behavior is a valid assumption. And usually I'll have the assumption that the molar volume of the vapor is much greater than the molar volume of the liquid. However, you should try to solve this problem the same exact way by trying to then solve for what the saturation pressure of water at 150 C is. In other words, have a larger temperature interval where the delta H vaporization assumption breaks down. If you try to go for that higher temperature, you wouldn't be able to assume this, and the answer that you get with the Clausius-Clapeyron equation would indeed be different from the answer that you get by looking at the steam tables. So that's all for this video. Again, the main points of this video were the derivation of the Clausius equation and the Clausius-Clapeyron equation for being able to predict phase change behavior from a known point of phase equilibrium.